the chat area, and you should be able to get the attendance form. Okay, so now that it is being recorded, so let me just start basically our discussion today. Okay, let's go with the implicit differentiation. So last Monday, I have basically uploaded a video on the what was the topic on Monday last time was the application of chain rule. Okay, so there were a few examples there. I hope you have gone through them, the examples, and you should be able to do the examples. So what we're going to do today is basically to look at this application of implicit differentiation. So what is implicit differentiation? So this is basically a general application, okay, where we can find the derivative or the differentiation of any functional form that is given to us. Okay, so before we do that, we need to somehow understand the notation that we use for different components in a function. Okay, if you look in the on the slides, you should be able to see that. So you are given. So this is the usual form, the usual notation of a function that is given to us, where we have the dependent variable y. So y is our dependent variable, okay, or output, and x is our input or independent variable. So, and if you remember from chapter 1, from what we have discussed, so x basically represent the set of domain, and y represent the set of range. So how do we define a function? A function basically says that for each element in the domain, in the set of domain, it leads to, or it corresponds, there is only one couple in the set of range. So one domain will only have one element in range. Okay, and we can rewrite this equation in this format, where we have defined this y is actually a function of x, f of x, f of x, and we can rewrite the equation like this, where this is a function where x is the independent variable. Okay, and we minimize the symbol, the number of symbol when we write either y directly, where y is f of x. So we know when we write like this, we know that y is actually a function of x. So this is y is actually a function of x. Y is the dependent variable, and it is a function. It is its value depends on x. So that's why it is a function of x. In this case, y is being used as both dependent variable as well as a function symbol. A function symbol where now y has become a function symbol where y is a function of x. Okay, so this is a bit about the notation, because later on we're gonna you have to remember. You have to remember that whenever we write y is never alone, because y is the dependent variable. Dependent variable means they cannot stand alone. They depend on something. They depend on another variable. So that's why whenever we write y, this is just to simplify the writing, but this y is actually y, a function of x. There is an x inside y. Okay, so I hope you get the concept when we put why we are writing y as a function of x, and this is applicable to any dependent variable. Okay, so far the functions that we have been dealing with, they only involve one independent variable. This concept can be easily extended to functions that involve two or more independent variables. For example, so if we have a function that depends, this function depends on two variables, x and y. So x squared minus 2xy plus 3y squared minus 5. So this is a function f that involves two independent variables, both x and y. Now, consider this equation, 3x squared plus y minus 2 equals 0. We can rearrange. Now we can modify this equation, okay, by rearranging such that we put y on one side and we collect all the other terms on the and put them on the right hand side of the equation. So we can simplify this. So this is basically, so we rearrange. So we put y, we want only y to remain on the left hand side, and we put all the other terms on the right hand side. Okay, so you should be able to see that these two equations are the same. These two equations are the same, where they are both, okay, function, the same function. Okay, the same function. It's just that here in the second way, when we write it like this, where we have basically defined that y to be the dependent variable. Okay, why did I and x is the independent variable. Okay, now the relationship, okay, between these two, in the second equation, the relationship, what relationship? The relationship between the dependent and the independent variables. Okay, so now the relationship here, the relationship is more direct. The relationship is more direct or explicit, where we have explicitly defined that, yep, y is our dependent variable, x is our independent variable. However, here in the first equation, the relationship is not that direct. Okay, it is indirect or it is implicit. Because we simply put them together, and we without any further deeper investigation, we cannot simply say that this is the dependent, this is the independent. Okay. Okay, so I hope now you are clear with regard to the concept of implicit and explicit. Okay, explicit relationship between these two variables, while this function, the relationship is implicit. Okay, implicit. Now, whenever we are given, okay, so let's just have a look at this example. So now this is an explicit, right? This is an explicit function. Okay, explicit function, where we have defined y is the dependent, x is the independent. Okay, so this is a directly stated. And if we are given this function, we can directly apply a rule to find the derivative. Okay, the derivative, and we can also find the corresponding value of y for each x. For each domain, we can find the range. Now, the equivalent equation define the same relationship between x and y implicitly. Okay, it is implied that these two are related, although they are not directly stated. Okay, they are not directly stated. Now, let's say we want to find the derivative of this explicit equation. Since this equation is explicit, okay, it defines the relationship explicitly, we can apply the rule, the power rule, right? The power rule here. So where y prime equals, so this is 0, we have negative sign, 3 multiplied by 2. Okay, 6x squared. Now, next step, what if we are given the same function but now in implicit form? Now, how do we find the derivative? Okay, now to find this derivative, we have to remember that this y, okay, it is a function of x. There is an x here, inside here, because y is the dependent variable. It depends on x. Okay, it depends on x. So if you want to find the derivative, okay, when x changes, of course, this term will change. This will not change because there is no x in 2. This is a constant. But since there is an x, because y depends on x, so when x changes, y would also change. So do not simply put 0 here. The derivative of y with respect to x is not 0 because y is a function of x. Okay, so try to imagine and rewrite it like this. Okay, so there is an x here. And so the next step is to differentiate both sides of the equation with respect to x. So we do it for the left hand side. and do it for the right hand side. For the right hand side will be easy, right? This is 0, right? d dx of 0 is 0. And for this one, since this is summation and difference, so we simply do them one by one. Okay, we can do them one by one. So see, we can do them one by one. Okay, step by step. Okay, so for the first term, what is the derivative of the first term? It will be 6x, isn't it? So we have 6x. And what is the derivative of y with respect to x? It is simply y prime. And this is 0. Okay, so now from here, we need to rearrange because our question, the question asks us to find the derivative, which is we need to solve for y prime. So y prime is, so since we have this, we simply need to rearrange where y prime, we put 6x to the other side, subtract 6x from both sides, so we have negative 6x. Now take note, this answer and the answer from the previous slide, okay, they are the same. Okay, they are the same. Okay, they are the same. Now, although the forms of the equations were different, where one is explicit, the other one implicit, we get the same answer, the same derivative, okay, for these equations using different processes. The first one, when we have explicit function, we simply use power rule, while for the implicit function, we need to do implicit differentiation. Okay. Now, why do we complicate things when with a new process? I mean, this is a very simple example. This is a very simple example where if we are given this equation, we can easily rearrange and put y on one side. However, this is not always the case. Okay, it is not always the case, especially during examination. Do not expect me to give you, I mean, like simple equations, such as this one. Okay, the functions, okay, many functions that will either be difficult or almost impossible for you to rearrange and to rearrange y explicitly in terms of x. So by applying this implicit differentiation, it allows us to find derivative for equation, okay, for this form, when it is almost impossible to separate them. Okay, if you, for instance, if you have I don't know, maybe let's say this is from your textbook, x, y equals x, x. I really need to x square y to the power of 5 minus 3xy plus 5 equals 0. Now, how do we find the derivative? Y prime equals to what? Okay, so can we rearrange? I mean, it is almost impossible to separate, to rewrite this equation in this form. Okay, very difficult. And this is why we simply should just apply implicit derivative. Okay, or you find the do implicit differentiation. Okay, for these functions. Okay, this is another example, okay, where we have this equation. Now, this is not a function. To separate such equation, y and x would be difficult. Okay, so let's say now the question here asks us how many tangent lines are there to the graph when x equals 0. Where is x equals 0? This is our x, our horizontal axis. So x equals 0 is here, right? At the origin here. So this is x equals 0. Now at x equals 0, so we have, so this is why this is, okay, so at when x equals 0, we have 2 points, right? Here. So what is the value of y here? 5, 1, 2. So this is 2, and this is negative 2. Okay, negative 2. How many tangent lines? So we have one tangent line here, positive tangent line, and we have another tangent line, negative, with a negative slope here. Okay, so we have 2. Now, why is this graph not not the graph of a function. This equation, the equation that defines this relationship between x and y, this blue line, the graph, it is not a function. Okay, so you should be able to know this by now. If you still don't know, so perhaps you need to revise, try to find the answer in topic 1. In topic 1, when we define what is a function. Okay. Okay, so let's try to do this example together. So we have this function, and we have been asked to differentiate implicitly. Okay, we have been asked to differentiate implicitly. Wait. Okay. So should we rearrange them? Put y on one side? Of course, this seems to be doable, but let's try to do the implicit differentiation. Okay, let's try to do the implicit differentiation. Okay. So let us try to do this together. So we have this. So how shall we? So we have basically need to differentiate both sides. Okay. So let's try to do this together. X squared plus y squared minus 25. We differentiate both sides. Okay. D dx of 0. Okay. Now this one we can separate them, right? Because these are simply summation, addition, and difference. So we have d dx x squared plus d dx y squared minus d dx 25 equals, what is the d dx of 0? 0. Okay. And here, so what is this? Okay. What is this? This is x squared. So what is the what is the derivative of x squared with respect to x? It is simply 2x. This one, now take note, there is a, so this y, if you, okay, you can rewrite it like this. Y is a function of x squared is 25. So whenever you are dealing, when you are dealing with this, so take note, okay, because we are dealing with y is a function of x. Okay, so there is an x here. So it is not simply 0. The derivative of y squared is not simply 0 with respect to x. So what do we need to do here? So we simply apply 2, we bring, because this is to the power of 2, right? 2y, and then 2 minus 1 is to the power of 1. And don't forget, since there is an x inside here, so we need to multiply this with, okay, let me just, so this is y to the power of 1. I hope everyone understood that. So this is simply y prime. Okay, y prime minus 0 equals 0. Okay, 0. Now this is when we apply the general power rule. The general power rule. Okay, the general power rule. Okay, so
Sir,
just discuss. Yes.
why here we put y prime again?
Okay, because of the power rule. Okay, if you remember, what is how do we apply the power rule? So the power rule says that if we have a function, if y is a let's say, let me just try to get back the slides for the, where did I put the slides? It's good to really know. So let me just let me try to find the slides first, and then is it somewhere? Chain rule. Six, 3. Somehow cannot find the slides. Let me try to find it. I think it's in topic 9. Topic 9, power rule. Where is it? Seems that somehow I cannot find it, but if I okay, this is power rule. 5. Six. Nine. And 2 is natural log. Product rule. Okay, this one. I think this was shown in the chain rule last term. Okay, composite function. It's like this one. Let me, is it? Not, open too much. Okay, just like this one. Okay. So when we deal with a composite function, okay, such as this, okay, so when we differentiate, because here, this is the original function given, okay, is this. So we have f of u is e to the power of u and gx is negative 3x. So for instance, if we are dealing with this function, so we have, well, what is our f of gx? So our f of gx will be e to the power of negative 3x. Now, if we were to differentiate this with respect to x, okay, differentiate this with respect to x. Now, of course, you can say that there is no x clearly stated here, but there is an x here. Once we put g of x inside, there is an x here. Okay, there is an x inside here. So that's why first we need to differentiate, okay, the function with respect to u, and then we need to differentiate gx, this one with respect to x. Okay, so just go back to our notes here. Okay. Okay, so that's basically explain why we need to differentiate this, why we need to have y prime, because in this y, so first of all, what we have done here, we simply differentiate this function with respect to y first, isn't it? We apply the power rule. So here we apply the power rule from here. So if you take note, if you just focus on this y square, this y is a function of x. So if we have y, which is a function of x square, so now we want to find so what is the derivative of this? Derivative with respect to x. Okay, with respect to x. We know x is inside here. So what we need to do, but this whole function is to the power of 2. So first of all, what we will do is that, so the derivative will then be, we're going to apply power rule. When we apply the power rule in the first stage, we're going to apply the power rule with respect to y itself. So that's why we're going to bring the power 2 multiply with y. And this is yx, the function of x. Now, would this be the answer to the derivative with respect to x? No, because we haven't differentiated anything with respect to x yet. We simply differentiate this with respect to y. So once we bring this 2 to the front, we are left with yx to the power of 1, right? 2 minus 1. And that's why we need to multiply. Multiply with, now we need to differentiate this y with respect to x itself. Okay, so that's why, don't forget, you always need to put this y prime minus 0. So now that we have this, so what next step would be, we have to rearrange such that we have y prime on one side. Okay, so here we have 2y multiplied by y prime equals, I'm going to bring 2x to the other side. So my y prime equals negative 2x divided by 2y equals negative x over y. So this is the derivative of this equation with respect to x. Okay. So of course, I mean the notation here would be more elegant. As you can see, okay, what we have done here together is the same. It's the same as here. Okay. So far so good. I hope. Hopefully this would come much clearer when we do more examples. Okay, so let's say we have been asked to find the, let me just erase this. Find the slope of the graph at x equals 3. Okay, so because this is the same, I mean, let me just make it a bit clearer. Okay, see that I cannot erase everything. Now we want to find the slope of the graph at x equals 3. Okay, at x equals 3, what is the slope, okay, of the graph? Now, we need to basically evaluate the derivative y prime when x equals 3. But when x equals 3, we still have y. We still have y, right? I mean, if you simply put this x into this equation, because this is basically the slope, right? The derivative, one of the meaning interpretations of derivative is that it is the slope of the graph. Now, when if at x equals 3, it seems that this equation is not a function, because when x equals 3, there is not only one corresponding y. So it seems that the value of x itself, I mean, like there are more. There are more than one y. I mean, so if you simply put 3 here, you have negative 3 over y. Okay, negative 3 over y. So to solve this, we need to first find the y values corresponding to x equal 3 by substituting and solving from the original equation. This equation, the original equation here. Okay, so replace that. So we have 3. So this is x squared. So replace x squared with 3. So 3 squared plus y squared minus 25. So this is 9 plus 16. Okay, so it's 16 squared. And the square root of 16 is negative 4 as well as 4. So we have 2 points. So we know that this equation, when x equals 3, okay, there are 2 y's. There are two y's. And that's basically already a hint that this is not a function, because one element in the domain, okay, x, has more than one corresponding set in the element in the range set, negative 4 and 4. So we simply substitute this, so we know that there are 2. Okay, now the slope of the graph, okay, when x equals 3, it seems that the graph, okay, is located at 2 points, and at each these 2 points, they have different slope. One is positive, the other one is negative. Positive 3 over 4 and negative 3 over 4. Okay, now further investigation. So let's say we have found that for x equals 3, there are 2 points on the graph with 2 different values for the derivative, or 2 different slopes. right? Two different slopes. So if we were to draw this graph, it is actually a circle. So this is where x equals 3 and we have 2 points at -4 and 4. So the tangent line, this is the first tangent line which is negative. So this one is negative. This is where the slope is -3/4 and this is where the slope is 3/4 positive. Okay, so this is a circle and it is not a function. So this is one application of implicit differentiation where we can find the slope of the tangent line easily. Second example. Okay, so now we have this equation. Okay, yxy squared plus x2 x squared plus 1 equals 0. Okay, and we have been asked to find the equation. So it's not just the slope, but the equation of the tangent line at the point where x equals 1. Now, to separate this, to separate y on one side, rearrange, okay, this is going to be difficult because this is a product and we have a square here. So to make our life easy, I mean, why don't we simply try to differentiate this equation implicitly, okay, implicitly. So how do we do this? So first of all, now, because the question asks us to solve, to find the point where x equals 1, so we want to locate. So first, the first thing suggested in this example is to locate, okay, the coordinate of x and y at x equals 1. So how do we do this? We simply replace all x in the original equation with 1, okay, with 1. So now we have this. So from this equation, so now we can find the value of y. Okay, as you can see here, there are two values. So we know that, so at x equals 1, we have 2 points. We have 2 points. 1, -1, and 1, 2. Okay, so this should already tell you that this is not a function because when x equals 1, it seems that there are more than one corresponding range element, -1 and 2. Okay, next step. We want to differentiate this equation implicitly. So how do we do this? So let's try to do this together. So now we're going to simply differentiate, okay, both sides with respect to x. So y minus x squared plus x squared plus 1 equals d dx 0. Now don't forget, all these y, they are function of x. This is a function of x, this is a function of x. So that when we differentiate this, so that when you have this d dx, so that so that here, so the first element here, basically this is just to remind you, to remind everyone that this is not 0 because y is a function of x. Okay, so do not simply replace it with 0. So now let's just try to, I'm not going to rewrite all of this again. So let's try to do this one by one. So what is the derivative of y when y is a function of x with respect to x? It is y prime minus. So now this is a product. So now we need to apply the product rule. So how do we apply the product rule? Because there is an x here and there is also an x implicitly in y. So we have to apply the product rule. So we have x, so d of dx y square plus, now y square d of dx x. Now this is the application of product rule. Okay, don't ask me to try to retrieve the slides because I think this is simple enough. I think everyone already master the application of product rule, right? When we have x in both terms. So we simply do them one by one. So first we treat x as a constant, we differentiate the second term. And then we plus, when we treat the second term as a constant and we differentiate the first term. Okay, and this is d of dx x squared. So what is the d of dx of x squared? I already said that I want to simplify the calculation. So x squared d of dx is 2x. And what is the derivative of 1 with respect to x? It is 0. Okay. So now let's just focus on the one that we have here, inside here. So we have, so this is x. Now differentiate this. So we're going to have x multiplied with, now first of all, we're going to bring 2 to the front, y. Don't forget, we multiply with y prime, right? We bring 2 to the front, So now this y is left with to the power of 1. And don't forget, y itself is a function of x. And because of that, when we differentiate this function with respect to x, it is the derivative, y prime. This y prime is the same as this y prime, plus, so we have y square. Now, d dx of x, this is 1, plus 2x equals 0. Now, open the bracket carefully. So we have, okay, I forgot to close this bracket. So y prime minus, now rewrite everything. So let's say we have y prime, and then this is 2xy. This is plus, this is minus. So we have minus y squared plus 2x equals 0. Now we need to collect the y prime. So collect all the y prime on one side. So y prime. So I have 1 minus 2xy, and bring all the other terms on the other side. So this would give me y squared minus 2x. So my y prime, the derivative is y squared minus 2x divided by 1 minus 2xy. Okay. Okay. This is the same. Okay. Now that we have find what is this derivative? This is simply the equation, the slope, the slope of the tangent line, isn't it? This is the slope of the tangent line. Remember, we have been asked to find where the equation when x equals 1. So this is the slope of this equation, of that equation when x equals 1. So we can replace x with 1, and we need to replace y with the corresponding value. Previously, we have already found, right? There are two values of y, -1 and 2. So we simply do that, and we will get two slopes. Okay. Now, first, let's deal with -1. So we simply replace this y with -1 and x with 1. So we get -1/3. This -1/3 is the slope of the tangent line. At this point, at 1, -1. Okay. Are we done yet? No, because the question asks us to find the equation. So use the point slope form. Okay, point slope form. This is what we have discussed. You should already master this. Okay. So we have y minus y1. So our y here is -1. And then we put the slope -1/3 and x minus 1. Rearrange, and this is the equation for the first tangent line. And repeat same process for the second point for 1 and 2. So this is the equation for the tangent line at x equals 1 for the other tangent line. Another example. Now, in this example, you have to be careful because we have basically defined x to be now x is the dependent variable, while t is the independent. T is time. Okay, t is time. Oh yeah, it is stated on your slides. So now let's try to do the implicit differentiation. Okay, I hope you don't mind doing this together. Without looking at your slide, just try to imagine, do the working in your mind. So we have this equation, t ln. So we're going to differentiate both sides with respect to t, because t is our independent variable. So we have t multiplied with natural log of x equals, differentiate with respect to t, we have x exponent to the power of t minus 1. Okay, so now this is, remember, x here, this x is a function of t. So I have t inside here. I have t here and t inside here. So here involve I need to apply product rule as well as the logarithmic rule, product rule, because there is a t here and there is a t inside x. So when we do this, so we're going to have to do this one by one. So t d dt natural log of x plus natural log of x d over dt t. Right? This is how we expand. We apply the product rule. We apply the product rule. What about this? We need to apply the product rule as well, because there is a t here and there is a t here, isn't it? There is a t inside here. So we have x d dt e to the power of t plus e t d dt x. Okay, and then we have minus 1, right? So minus d dt 1. Okay, so this also involve product rule. Product rule. Next is where we need to apply the natural log rule. Okay, the natural log rule. So this would be 1. So how do we differentiate this? So first of all, we differentiate this with respect to x. So this would give us 1 over x, right? The logarithmic rule. And don't forget, there is a t inside. So that's why we need to multiply this with x prime. X prime. Because we are differentiating this term with respect to t. And there is a t inside. Okay? Plus. So this one, we treat it as a constant. What is the derivative of t with respect to t? It is 1 equals. So now this is x. Differentiate this with respect to exponent. So now we apply the exponent rule, et. We get et itself plus et, and this is x prime. X, when we differentiate x with respect to x, we get 1. And then don't forget, there is a t inside here. So we have x prime minus 0. Okay. So we have t x prime over x plus natural log of x equals x e t plus x prime e t. Okay, what's next? Okay, our main, you have to work on this, rearrange this until you can rearrange x prime on one side. Okay, on one side, while the others put on the other side. Okay, so let's just try to collect term here. Okay, I'll just leave this exercise to you. Okay, because I think from here it should be simple enough. You should be able to rearrange all these and collect the x prime and put them on one side. Okay, put them on one side such that, fortunately, this one is I need to you can see the answer on your slides, right? So try to make sure how you can rearrange this until you get x prime. Okay. So, and don't forget what you have found. This is only the slope, and you are asked to find the evaluate, find the derivative at a specific point. So you have been asked to basically, so this is the slope that we have found previously. So assuming that, inshallah, you will be able to get this, you should be able to get this. Okay. Can you just give me a minute? I just need to put on hold for a while. Sorry for the interruption. Just that I had an emergency call. Okay, what did I do here? I wanted to leave or... Okay, so we were already at the last slides. Okay. Okay, so this is the slides. Sorry, this is slide. So this is the slope, okay, of x prime. Okay, and what you need to do next is simply to evaluate this, at this at this coordinate, okay, at this coordinate where t equals 0 and x equals 1. So what you need to do is just replace or substitute t equals to 0 and x equals 1. Okay. Okay, and that's basically the end of implicit differentiation. So the next topic, okay, the next slide is on this related rates. Okay, this is simply the application of all this differentiation, okay, with regard to velocity, okay, with regard to also business and economics, when we have cost and revenue and profit. Okay, so this is just the application of implicit differentiation. Okay, implicit differentiation, as you can see, you have this type of cost function, okay, and how you're gonna then do the implicit differentiation and solve for whatever problem that has been given to you. Okay, so I'm going to leave all this to your own responsibility, because this is simply the application of implicit differentiation for different areas, velocity, business, revenue, cost, and profit. Okay? And similarly, the other application, okay, would be on this elasticity of demand. Okay, for elasticity of demand, it also involves the application of differentiation, including implicit differentiation. Okay, this topic basically will also be discussed in your principles of microeconomics class. Okay, principles of microeconomic class, where when we raise the price of a product, okay, it will of course affect the revenue. Okay, sometimes when price goes up, okay, revenue would go down, but sometimes when price goes up, revenue can also go up. Okay, so this basically lead us to this concept of elasticity of demand. Okay, to understand the relationship between price, demand, and revenue. Okay, now this is simply the definition. How do we define relative change? Now, relative change is simply when we find them in proportion, we find the derivative and we divide it, okay, with the original value. While the percentage, we simply take the relative change, we multiply it with 100. Okay, we reply it with 100. Okay, this is example of the application of relative rate of change, okay, and the percentage rate of change. Okay, there is a typo here. This should be T. This should be T here. Okay, I'm going to leave these applications to you as well. For elasticity of demand, okay, this is how we define the elasticity of demand. When we have quantity, X is quantity. Now, quantity depends on price. Is a function of price. So let's say this is our price demand equation. Now, to find the elasticity of demand, what we need to do is that we are investigating the relative rate of change of demand divided by the relative rate of change in price. Okay, in price. Okay, so we can simply apply the concept of derivative, okay, where the demand function, which is a function of price, we can differentiate, okay, find the derivative, the rate of change, the relative rate of change. Okay, so this is what we have defined, right? The relative rate of change. So here we find the derivative of the demand function itself, and here we find the derivative of the price itself. How much would demand change divided by how much, okay, has the price changed. Okay, so from the definition that was given earlier, so this is simply the derivative of the demand function, okay, f prime of p over f of p, the original demand function, because whenever we are investigating change, we always need to refer back to the initial or the original value, and then the change in price, the relative rate of change in price, okay, the relative rate of change in price, which is 1 over p. Okay, how much did the price changes? Okay, so we can rearrange this such that, you know, we can bring this p up in the numerator. So this is basically the definition of elasticity of demand. Okay, the elasticity of demand. Okay, let's say we have this example. Okay, we have price and demand X, okay, related by this. So this is the equation, quantity, okay, and price. Okay, so if we were to, we have been asked to find the elasticity of demand and interpret each of the following. Okay, each of this. So let's try to do for this. So we need to simply rearrange this equation. Okay, we express the demand as a function of the price. Okay, so this is our demand equation, our demand function. So we're going to collect all terms. I mean, this is simple, right? We simply collect X, okay, put it alone on the left-hand side, and we put all the other things on the right-hand side. So we have 10,000 minus 500P. Okay, you should be able to see that there is a negative relationship between, I mean, this is the law of demand, right? If price goes up, quantity demanded would go down. Okay, would go down. Okay, and also this equation put a constraint on price. Price cannot be greater than 20. Okay, price cannot be greater than 20. What happens if price is greater than 20? Then demand would be negative, which is, I mean, which is not realistic. It doesn't make sense to have negative demand. Okay. Okay. So it is a decreasing function, okay, law of demand and stuff. So let's try to do this. So how do we find this, the elasticity of demand? So we have P. So what is the derivative? F prime of P, it is, so here we have, so if this is, this, so if X is F of P, 10,000 minus 500P, so F prime of P equals negative 500. So we have negative 500 here. So P multiply with negative 500 and then divide everything with the original function itself, which is written like this. 500 multiply with 20 minus P. So we can cancel these out, 500 and 500. And we have negative sign here, cancels out this negative sign. So we have P over 20 over P. So this is our elasticity of demand for this specific relationship. Okay, so now we have been asked to find this, E of 4. So we simply substitute P. When price is $4, the elasticity of demand is 0.25, which is less than 1. What is the meaning of this? How do we interpret this? Now, it's just that here your textbook, the slide use 10%. I mean, the standard interpretation is to use 1%. Okay, so if the $4 price, if currently the price is $4, okay, it's let's say initially the price is $4, and then if you want to increase the price by 1%, then demand, if price goes up by 1%, then X would go down by 0.25%. Now this actual value corresponds to 1% change. It's just that your slide used 10%. So 10% means 2.5. Okay, 2.5. Now, when price is $16, and if price changes, okay, I mean, this is, I use the notation go up, it can either go up or go down. I mean, just to make it the interpretation easier. So when price is already $16, and if the price changes, okay, by 10%, demand would change by approximately 40%. In this case, if you are selling a good which is the price is already $16, and let's say you raise the price, by 1%, demand would go down by 4%. If the price go up by 10%, demand would go down by 40%. Okay, by a bigger value, bigger amount. $10 equals to 1 means this is a unit change. If price changes by 10%, demand will also change by 10%. If price go up by 1%, demand will go down by 1%. Okay. So these different values, as you know here, why are we comparing this with 1? Because 1 means that we have a exactly one-to-one relationship. One-to-one relationship. You raise price by 1%, demand goes down by 1%. But when the elasticity is less than 1, increase in price, we increase the price by 10%, but demand only go down by 2.5%, which is smaller. This is what we term as inelastic. Even when price goes up like crazy, I mean like with such a big amount, demand only fall by a small value, by a small amount. Okay. And in other words, in this case, people are not sensitive to change in price. It will not really affect their demand. They will still buy that good even when the price has gone up. And this is what we term as inelastic demand. While in the B case, price is already expensive, it's already high, $16. And if you were to increase the price by 10%, surely demand would fall by a bigger amount. And in this case, people would be sensitive because it is already expensive enough, $16. Okay. So I'm going to leave all this reading to you. Okay, this concept of inelastic demand, because it is not sensitive, because when the elasticity is less than 1, we describe it as inelastic demand because the consumers are not sensitive to changes in price. So the conclusion is that when we have inelastic demand, a price increase will increase revenue. So this is a good strategy. If you know that your product have inelastic demand, you should increase your price so that you can have more revenue. The opposite is true for elastic demand. When elasticity is greater than 1, you are having elastic demand, where demand is sensitive to changes in price. And if you have this, price increase will decrease revenue. Okay, when people are sensitive, if you want to have higher revenue, you should lower your price. Okay, and then you need elasticity when the elasticity equals to 1. Okay, this example, I'm going to leave this example to you because it is simple enough. It should be, so try to spend some time to do this, go through the examples on your own. And I think that's basically all for today. Okay. So I hope to be able to finish grading test 1 by this week. You need to give me a bit of time. And also, please be prepared for the next quiz. I plan to give you a quiz on what we have discussed for since last week and this week. In a quiz, inshallah, by either tomorrow night or Thursday night. I mean, just like always. So I think that's all for today. If you have anything, you can just send me email or WhatsApp. And see you next time, inshallah. Okay. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Thank you, sir.
Welcome.
Thank you, sir.